And the chat is also streaming. We have a few people saying how we miss the snacks and beverages we usually have for this talk.
Would you recommend that we have YouTube Live open as well, or is
No,
that okay?
I think that will interfere with. I mean, you can have it in a separate window. Make sure you mute it if you have it running in a separate window.
But it's just going to add to your, if you have internet issues, it's just going to be that much more bandwidth.
Okay.
So we're live, by the way.
Yep, I can see it. And I think Glenn and I need to have YouTube open because we need to keep an eye on the chat channel, but you guys can just take the show. So
Yep, 16 viewers. 17.
cool. Can you see the list of viewers anywhere?
I don't know how to do that.
Okay. Okay.
Know how to do that.
That's fine.
Will you let us know if there are questions during the presentation, or are we saving all questions for the end?
So given that we are trying this virtually for the first time, let's keep them to the end. Usually when we are in the same room, it's more easy to coordinate if people just want to ask questions as we go. But for the sake of this talk, let's keep them to the end. I will mention all that in my introduction.
Oh, Connor and Anna, just say next slide when you guys want to switch this slide.
Okay, I guess we can get started. Hi everyone, we are streaming live from our homes to do this general meeting that San Jose Astronomical Association has every month. This is something we typically do every full moon weekend, and the idea behind it being that we cannot go out and look at a lot of stars on a full moon weekend, given how bright the sky is. So we have our board meeting and we have a general meeting where everyone is invited. It's open to public, and we can. You don't have to be a member to attend it. And we do an astronomy talk where we have guest speakers come in to give a talk for us, followed by a question and answer session. We are going to follow that same format today. But before I get into the talk for tonight, I just want to mention that this is something that San Jose Astronomical Association is trying new, and we are a very active social club. So adapting to COVID-19 shelter in place has definitely been a bit of a challenge, but and astronomy is not something that you can always do from sitting at home. But we are trying everything to take it to your home. That's exactly the idea behind this talk today. We have started taking a few of our events online. We have a special imaging group. Their events happen every month as well, and that talk is already virtual. Star parties is something that we are currently playing with as to how to do that virtually, but we definitely intend to make that happen as well. So if you have any ideas, and more than that, if you have any feedback for us, please feel free to write to any one of us. You can go to sjaa.net, or you can find us on Meetup and join the Meetup and send us your feedback there. We would love to hear back from you as to what else we could do, what other events we can provide to you as in a virtual format, or how we can improve the existing events that we are trying to deliver right now. And so I think just a quick thing I would like to mention is uh, like the upcoming events. So I think we are trying to do a star party, a virtual star party next weekend. And then we are also doing a solar observing event, which happens once a month on a Sunday. Again, these are telescope observing events, so we are playing with the format right now. But while we are trying to decide how to do it and figure out how to do it, we are keeping the information up to date on the meetup. So please go to the meetup, find us there, and look at our calendar. And a YouTube streaming link of any kind will be provided on the meetups specifically for that event. And today, since we don't have the regular in-person interaction, we have a chat channel open. So feel free to drop any notes there, any questions you have for the speakers, or any generic questions about SJAA, and I can try to answer them during the talk or after the talk, whichever way works better. So without further ado, let's come to the talk for tonight, which is we have three cool kids, as I would like to call them, from Saratoga High School, giving us a talk about a radio telescope they put together. I'm very excited to hear about this because radio astronomy is not something that is very accessible for amateur astronomers. And if this talk definitely can give us an insight into how it can be made accessible to amateur astronomers. And Karen, Anna, Connor, all of them go to Saratoga High School right now. They are all part of this astronomy club at the high school. And I think I will let them start now. So Karen, do you want to start?
Yes, thank you. So hi everyone, I'm Karen. I'm the president and founder of the Saratoga High School Astronomy Club. And our talk today is titled Saratoga High School Astronomy Club Radio Telescope Project. And this was essentially kind of low cost exploration into amateur radio astronomy that we did with our club kind of last fall throughout early spring. And I'm here with Anna and Connor. You guys want to introduce yourselves?
Hi, I'm Anna Dimchenko. I'm the treasurer of the club. I've worked with Karen and Connor on this project. I worked mostly on software.
Hi, I'm Connor. I'm a senior in the astronomy club, and I worked mostly on the hardware side of it.
Okay, so we can get started. First, in case you guys are wondering what this 21 centimeter hydrogen line that we basically sought out to detect with our homemade radio telescope is. So the kind of background of this phenomena is when an electron transitions between energy levels in a neutral hydrogen atom, as you can see on the diagram on the right, it basically emits a radiation with a wavelength of 21 centimeters, and which is equivalent to a frequency of 1420.405 megahertz. And then this radiation is really quite useful to astronomers because it's like a lot of radio waves. It can penetrate like interstellar dust and easily pass through kind of the universe. So we can basically detect it even with kind of the low cost like radio telescopes that amateur astronomers can make. So why is this 21 centimeter hydrogen line very useful? Well, first of all, as many of you may know, hydrogen is the most abundant element. On the left image here, all of the gray portion is the hydrogen composition of our universe. And then astronomers are currently using the hydrogen line emission for kind of purposes such as studying the dark ages. So the dark ages is like a very special time of period after the Big Bang, where it's basically characterized as being before the first stars or planets were born. So really the only thing that was there during that time was hydrogen, which makes this hydrogen emission line like such a useful tool, because we couldn't really detect anything else because there were no stars, there were no planets. And then another project that is quite accessible to amateurs, but is also widely used by professionals, is mapping the structure of like the Milky Way or other galaxies, which can also be done using the hydrogen line emission. So now we're going to be talking about hardware and assembly and how we make this up.
All right, so for the materials, we used a 4-inch thick polystyrene insulation board, and this could be found at basically every hardware store, and it's used to insulate. And one 4x8 foot sheet should be enough for our aperture, but obviously if you wanted to make it bigger, you could have more sheets. And then for wood for the base and to support the horn, we used wood that we bought at Home Depot, and also wood I had left over from an Eagle Scout project. So we used 2x4s, 1x3s, and 1x2s. And we used wing nuts in order to change the angle of inclination. And this was along with T-nuts and bolts. So basically, like the bolt went into the base, and then the T-nut went into the base, and then the bolt went through that, and then you tighten the wing nut so that you could have adjustable inclination, and it wouldn't fall back. For conductive tape, so in order to connect all the panels together, we would put a conductive tape between the panels, and if it's not conductive, it won't work. So it's very important. It's used in bathroom fans. So it's usually like there's like a tube that goes like from the bathroom fan out to the exhaust vent, and it's usually taped with conductive tape. So you could find it in most hardware stores. A 1 gallon rectangular can. Basically this can, I believe it's used to store oil. But what we used is we cut the top off and then used that as the to store for the bottom part of the horn. And then duct tape was non-essential, but it definitely helped make it a lot more robust. So we put the duct tape on the outside of the horn, and on the inside of the horn, it has the conductive tape. On the outside, it has the duct tape just so it doesn't fall apart. But the duct tape is overall optional, and you can probably get away without having it. Wood screws. So to put the base together and to put the holder together and all the wood parts together, you need wood screws. We used kind of wood screws that were on the longer end, and we had a bit of a problem with splitting the 1x2s. So preferably smaller screws. I think like 1 inch, 1.5 inch should work fine. Thin aluminum sheet. So this sheet is basically to connect to the can to the horn. It needs to be bendable in order to bend to that to the angle of the horn, and basically smaller nuts and bolts to attach the can to the aluminum sheet to the horn, and then a brass metal rod in order to pick up the signal. And yeah. So in the next slide, assembly. So the first thing we did is we cut the foam into the 4 trapezoidal pieces. This was a little bit difficult given the tools we had, but we basically used like a knife, and since it wasn't deep enough, we went back on the other side. But there are better ways to do it, which I will talk about later. So we cut those pieces out. They're each like trapezoidal pieces. And then next thing we did was we assembled the wooden base and holder. This can be used with the wood. The base is made out of like the 2x4s, and then on the sides are the 1x3s. And then basically it was kind of optional. It was pretty sturdy beforehand, but we also put in like diagonal 1x2s in order to connect the 1x3s to the 2x4s to give it a little bit more strength, but you could probably do it without that. And then we affixed the inclination hardware to the attach the holder to the base. The holder is the rectangular wooden part that goes around the horn and basically holds that horn in place. And then the base is the part that stays stationary on the ground. And we put the bolt through and the T-nuts onto the base. And so we could adjust that inclination. And then we attached the foam pieces together with the reflective side in and the inductive tape on the inside edge. Since our cuts weren't perfectly even, you kind of had to like put it up on a slight angle and then put the conductive tape down on that and then fully fully bend it into that 90 degrees in order to get that. But if you do have like a perfect like laser cut, you could probably just like put it down on a flat surface and then tape it and then fold it up. And then after we had finished all the inside with the conductive tape, we put the duct tape on the outside to make it more robust. Of course, that's optional, but it definitely helped. We drilled the holes into the can with the hand drill and the aluminum sheet and the foam. And we bent the sheet. We used we have a tool at our school that was used to like bent polycarbonate, where you would like put the polycarb and then you put some clamps down and then you would bend it and like heating it with a heater and then but basically we also found that you could use that to bend the thin aluminum. So we just put that in, just bent it, and we kind of eyeballed it using a protractor to try to get the right angle. But there are probably more exact ways to bend it. And then we used the smaller bolts and nuts that we had in order to connect the aluminum sheet to the can and then the can to the horn. So basically we had to put because of the angle of the aluminum sheet bent, we had to put the can in through the top. Yeah. Next one. All right, assembly. Yeah. Right. Yeah, construction process. All right, so here we have a couple images of the process we went through to build it. So on the left, you can see a view from the outside. This is on the right. You can see the can, and on the left, you can see the foam horn. Now, basically, on the right, you can see a view from the inside of the horn. So inside that foam part, looking into the can. And on this one, we haven't put in the bolts yet. But basically, where those holes are, you would put bolts through to connect it to the horn. All right. And then also on the left image, you can see the duct tape we put on the outside for extra stability. Next slide. So certain difficulties we did have, and that could probably be fixed with better tools or just doing things differently, is the drill kept slipping while trying to drill the aluminum can. one way to probably fix this would be to use a center punch to first punch like a dent into the metal, and then use that to drill without it slipping. And I think that would probably be fixed. So cutting the 2-inch foams straight. So yeah, it was really hard to get straight with our tools because we had like a really shallow, thin knife. And but there are like probably better ways. Like you can either use like a laser cutter with proper ventilation. Of course, polystyrene, very toxic. But or like jigsaw or something. Attaching the bolts to the from the sheet to the can. So it was a bit hard to reach inside because you would have to, on one side, you would have to tighten the bolt, and on one side you have to tighten the nut. But usually you can just use one hand on each side. But since there's a big horn you have to get around, you would have to have one person in tightening the side inside the horn, and one person on the outside of the horn tightening that side. Attaching the bolts from the sheet to the can. Yeah. I went over that. Bending the sheet metal to the right angle. So we used the protractor and kind of eyeballing it, which kind of worked because since it's pretty thin aluminum sheet, it didn't need to be exact because when you tighten it with the bolts, it'll basically go to the right angle. But of course, it's not super exact. So we didn't have big enough drill bit for the electronics in the can. There's basically like a 2¼ inch hole that where the electronics go, the brass rod into the can at the focus point. And it was really hard to get that hole because we didn't have a big enough drill bit. But a pepper bit would probably help a lot, just because, yeah, even if you had like a really large bit, it would probably slip because it's aluminum. And finding the parts, some parts were hard to find, particularly like the electronics, but many of them you can find at any hardware store. All right, so and this is the picture of the finished product. On the left, you can see the base, the holder, and the horn all together. And you can see where it pivots. There's the wooden part that holds the horn, and there's the base, and in between that, there's a point where you can adjust the inclination. In the middle is a view from inside the horn. You can see the brass rod in the very middle that's going in through the hole, the larger hole for the electronics, and you can see all the bolts to attach the foam horn to the aluminum sheet, and the aluminum sheet to the can. And on the right is another view from inside the horn, but a little bit farther back. And this is a view of the final setup with the computer, all the electronics, and the horn. All right.
All right, so moving on to electronics and software. Next slide, please. So the main two components that were vital in our construction of the telescope were a low noise amplifier and a bandpass filter. These we ordered from Newelec as a combination electronic device. So essentially what this does, the low noise amplifier amps up the signals that we want in the range that we're looking at, while the bandpass filter tries to filter out some of the excess noise and tries to make sure that we don't have too much extraneous data. We use a coaxial cable to connect this setup to a RTL SDR dongle, which was ordered through Amazon. So initially for the coaxial cable, we used a 10-foot length. However, we then switched to a 3-foot cable because we were observing some excess noise the longer length. We suspect that this was because of the increased capacitance. The RTL SDR dongle is just a simple generic USB device used for software-defined radio as a whole. It's not specifically meant for radio astronomy or a specific purpose. Essentially, you plug in, download the necessary software, and you can have access to a wide range of radio settings and observations. To power this setup, we initially use a USB power pack. Then we switched it to a homemade 4.5 volt battery pack instead. This was because, again, we suspected that the USB was causing noise. And then finally, an optional element of our setup was an oscilloscope, which was used to verify that we were receiving correct data without having to connect all of the electronics to a computer. However, given the pretty high cost of having an oscilloscope, it's unlikely that you'll need this as part of the setup if you'd like to recreate this. Next slide, please. So moving on to software, the primary program we used was SDR Sharp. Again, this is a software-defined radio program which allows us to set the parameters for the observation. In our case, we use a central frequency of 1420.405 megahertz at the hydrogen line, and our sample rate was 2.4 megasamples per second. As you can see on the right, here's a window of how the program would look like when running. Ideally, you would want to see a spike at that central frequency. The sampled screenshot does not have the radio telescope plugged in, so all you're seeing is basically noise. In general, SDR Sharp, like the dongle, well, it's part of the dongle setup. It allows you to perform a lot of different things with software-defined radio. Next slide, please. So to continue our explanation of software, the secondary program we used was CFRID2, which is a Python script written by Michel Claassen for similar observation of the hydrogen line. What it does is it performs a fast Fourier transform to refine the data collected using the SDR dongle by outputting data files every 5 minutes. It can collect such data for up to 24 hours and allows us to use a computer to get data, which is much easier to graph than having to manually sift through the data collected through SDR and trying to make sense of it all. We also briefly looked into SOAPy SDR, which is a library supporting software-defined radio made for Linux. So we were running into some errors of CFRD2, as I'll explain later. So we ended up looking at Linux temporarily as a solution to some of the difficulties we were facing. However, we ended up working things out with CFRD2. I still do think that SOAPy SDR is a pretty viable and perhaps a better, it has a wider set of applications than CFRD2 in terms of radio astronomy. For example, you could map like the branches of the Milky Way or something else with the system. So definitely worth checking out if you're interested. Next slide, please. So as I mentioned, our greatest difficulties with software were the restrictions and requirements set by our programs. CFRD2 was initially written for Windows 7 computers. However, understandably, most of the computers we had on hand were Windows 10. So the problems this caused, while we're unsure of the exact specificities, what happened was that Windows 10 removed certain accessibility to data that CFRD2 needed to run and process the data collected from SDR. And essentially, it was running into a Python error as shown up top. So one of the attempted workarounds we tried was installing Windows 7 as a dual boot, but we still encountered the same errors. We do not know the source of the errors that we encountered on a dual boot, as in the interest of time, we moved on to just contacting the writer of CFRD2, Michel, on possible changes necessary to make CFRD2 work on Windows 10. Eventually, we figured a solution out, and it was ready to be used to record data. Next slide.
Okay, so now I'm going to be talking about how we actually conducted observations with our radio telescope and our software. So essentially the method of observation we use is called a transit scan. So basically what you do is you set up your radio telescope, like ours, and since our radio telescope isn't like a professional one by any means, it cannot like track the sky over time, but rather in a transit scan, you just fix your telescope at like a specific area of sky. And when you observe over like 24 hours, for example, the sky itself, as we ourselves, the Earth, are rotating, you'll naturally observe like the entire cycle. And then as Anna mentioned, our primary method of collecting data is the fast Fourier transform. So essentially what this does is it converts a time domain into a frequency domain, which is what we are interested in. And then as for how we knew like where the coordinates of where we were pointing our radio telescope, we used an app called Skyview. And so basically Skyview allows you to see either the right ascension or declination, or also the azimuth and elevation of the coordinates. And by aligning that with our radio telescope, we could basically know where we are pointing the telescope. And then we also use an elevation finder, which is pictured down here. This is a more like accurate method of measuring the elevation as a coordinate than Skyview. And then last note for observing, in case any of you want to do future radio astronomy observations, we found that we needed to give the SDR dongle around like 25 to 30 minutes to warm up and become like stable and reach thermal equilibrium, because otherwise if the dongle is still fluctuating in temperature, that's going to generate excess noise that we don't want in our data. So here's, I'll run through a quick procedure for how we would conduct an observation. So first we, of course, set up all the equipment in the radio telescope. And then next we use the Skyview app to point at an elevation. So on the right, you can see here, this is what the interface for the Skyview app looks like. And this tells us right ascension declination. Note that right ascension declination changes for like the same area of sky over time. So we mainly prefer to use azimuth and elevation. And then next we'd open SDR Sharp, set the parameters that Anna described earlier. And then we click play, and then after that we'd open Task Manager to close SDR Sharp because we have our parameters set already. And then once we close that, we start CFRD2, and then immediately you should notice that a new file, it's always called NRD raw, is written in your folder. And then after every 5 minutes after that, a new file will be written. So we'll go NRD 0, then NRD 1, then 2. And then in each file, there's a list of 2048 numbers. So it will look kind of like on the right. And then CFRD is the software that performs the actual fast Fourier transform. And then after that, you can just leave the radio telescope outside for however long you want to observe for. And then make sure to save the files to a separate folder. And then next, we recorded something called a baseline. So essentially, to record a baseline, we would point the radio telescope at the ground or somewhere with no signal. And why we would want to do this is because the equipment, the electronics we use, the computer, all of that has noise itself. And we don't really want to include this noise in our signal data. So what we do is after we record our baseline data, we can effectively like divide it out to just obtain the actual signal data. So you can record it, just repeat the above steps, and then you don't have to leave the telescope out for like 24 hours or anything, just around 1 hour to get stable and like accurate files. And then save these files as well, and then combine them with the above, and then repeat if you want to have more accurate data. So now we're going to be talking about how we analyze the data we collected, and then takeaways.
So here are some examples of graphs that we collected using our data. At the top right, you see our graphs collected for a long cable, the 10-foot cable previously mentioned. So this slant is of unknown origin. So we suspect it was something to do with the higher capacitance of the longer cable. So, and then relative intensity, the Y value on the side is just the data collected using CFRD divided by the baseline times the scaling factor. Note that the x-axis is the bin number in CFRD2, so x is equal to 1024. That actually corresponds to the central frequency we're looking at, 1420.405 megahertz. Down at the right is an example of data that's noticeably cleaner and more closely matches what we were expecting. So the fin spike at 1500, as you can see, is most likely some form of electronics data. When trying to set up the telescope at home, one of our group members observed a sudden spike that was very close to 1420, but abnormally high considering the sort of vagueness of where we were pointing the telescope, even despite our best efforts. So it turned out that after some troubleshooting, that it was just a specific computer that was running upstairs that was causing the false marker. So in general, it's good to know what forms of radio frequency are occurring where you have the telescope set up and try to make sure that you have no such false markers. And then all of the graphs to the right were composed using Google Sheets for ease.
Oh, and I want to add something quickly to what Anna said. So Anna mentioned like the radio frequency interference we observed. So this is like this spike and this spike. So how we know it's interference, because a lot of times it's hard to find the origin of the interference, especially as there are a lot of possible objects that could be causing it. Well, normally interference looks something like this, where it's extremely narrow, very high peak. And so we can distinguish this from the actual hydrogen data here, because you can see like the hydrogen is more of a broader, wider kind of signal peak than the interference.
So the Doppler shift. So Doppler shift occurs because of a relative movement to a source. So if you've ever been on a street and there's a fire truck going by or like a police car, you can hear the sound of the sound is higher when it's coming towards you, and it gets lower when it's going away from you. It's like zero, right? And that's due to a Doppler shift in sound. Now, in the cosmic scale, we're talking about a sort of Doppler shift in light. As objects are coming closer to you, they're blue shifted. And as objects are going farther away from you, they're red shifted because they shift towards that end of the spectrum due to their relative movement. Yeah, and that's reflected in our data.
Okay, so now I'll be talking about a 24 observation that I did a while back. And so first you can see on the left is a graph. We use a Python script that was obtained from Mikhail Klassen's website, peric.eu, to basically help us analyze our data and produce like a better looking graph than was made from Google Sheets. So this observation was conducted over 24 hours, and we pointed our radio telescope at the Cygnus A region, which some of you may have heard of. And then so you can see on the x-axis is essentially, it says 5 minutes from start, but it's essentially time, because we know that CFRD collects one data file, which is the numbers on the axis here, every 5 minutes. And so we can basically treat it like time. And then the y-axis is uncalibrated. So it's the y-axis isn't incredibly significant at its current state, but we treat it more as like a relative intensity kind of unit. And then so here you can see two very like noticeable peaks. And so these are basically confirming that we accurately and correctly detected the hydrogen line. And then next, so some more graphs. So on the left, you can see a more specific plot of a hydrogen line detection. And as Connor mentioned earlier about the Doppler shift, you can actually observe it in our data collected here. Because if you notice at 0, which is corresponding to the 1420.405 center frequency, it's actually shifted about like negative 0.05 off, which is the center of the hydrogen peak we're looking at right here. And so this bit kind of shows we did detect like a Doppler shift. So it is important to consider when you're collecting data. And then on the right is just a contour map we plotted for fun. So a contour map basically, again, shows like the relative intensity by using color, which is a more sometimes more intuitive way of looking at it. So as from the last slide, we had the two peaks, and then here you can see basically the two peaks shown through the higher intensities here. And so this is the map we have for the 24-hour observation.
So in terms of takeaways and advice we'd have for future amateurs wishing to pursue such a project, the number one thing that we really need to consider is patience. So, I mean, as mentioned before, we had plenty of issues with software and hardware, which took a while to work through and find a solution for. We have to be flexible with parts and instructions. Some of the materials that we planned to use were not always available or didn't turn out to work as well as we expected to. So we had to adapt to that in some way.
Yeah, so using available materials can cut down costs a lot. Like we used some extra wood I had from a Eagle Scout project. So basically, just we had to make a lot of changes, and we just tackled the project head first. Obviously, there was not everything really worked out the first time, and we had to sort of change the way we did stuff, and figure stuff out. Like there was a lot of software issues. And there's a lot of resources that exist on the internet. So we used a lot of other previous projects that were similar to sort of get an idea of where we should head. And our project is sort of a combination of multiple projects that had existed.
And then also one like huge piece of advice for any like potential budding amateur astronomers, although like you should be like patient, be careful when you're working through things, it's sometimes just beneficial to just directly tackle a project, and because there's like always endless stuff that you don't understand. Like for us, none of us had very like significant software backgrounds, even though we knew some coding. So figuring out like fast Fourier transform, figuring out libraries, figuring out all of these things, we kind of were able to learn along the way. So it's so a project like this is really a good start for anyone interested in like radio astronomy or even just amateur astronomy, because it's it combines like construction, software, and observing and astronomical concepts.
So future improvements that we would make if we were to do the project again is we would use a jigsaw or laser cutter, get straighter foam cuts. We used like a knife, and since it was too thick, we used a knife on one side and then we did a pass on the other side after that was measured out, and it was really sort of jagged. So jigsaw, you basically just put the top of the jigsaw on it, and it creates like a straight 90-degree angle. And also a laser cutter would obviously get super precise cuts. Changing the horn design to be more accurate and sturdy. We had maybe like one wooden bracket that sort of holds it together, but some other people have done like two different brackets, like a higher bracket and then a lower bracket, and to make it more sturdy. And you could probably also find better ways of keeping it together than like duct tape. And a better way to measure the angle of elevation. I mean, the only way we could really measure it was like a protractor or whatever, and kind of just eyeballed it. It wasn't super exact. A larger horn for better signal. We used basically all the material we had from one sheet of 4x8 foam, but if you use two sheets or one sheet or four sheets where each sheet is its own panel, you could get pretty big with this sort of design.
And then in regards to software, we definitely could also look into writing Python scripts that better suit our observational needs. Obviously, a lot of the programs we use, many of which were based on Mikhail's work, were specifically targeted towards graphing the hydrogen line. If we had more time outside of student life to work on this project, we'd probably definitely look into writing our own scripts to observe what we wanted. Like, as I mentioned before, we could, using this telescope, we could also plot the shape of the Milky Way or compare hydrogen emissions from different regions.
And then also one quick future improvement we should also investigate would be a more accurate way of determining the coordinates of where we're pointing our telescope than Skyview. Because if any of you have ever used Skyview before, a lot of times you just kind of hold your phone up and then you just, when you're observing, and point at the sky. And so how we, this is probably one of the most like error prone parts of our observation, because we try to like hold our phone to align it with the radio telescope, but even just like changing the phone's orientation a slight bit would cause like a pretty significant change in the coordinates that we recorded. And so we're the elevation finder did help resolve some of the elevation error, but as for azimuth, we're still looking for ways to improve that. That's relatively low cost. And then we'd like to say like a very special thank you to the Society of Amateur Radio Astronomers, or SJAA, also to John Wallace, whose article was basically like the inspiration really for our project and a reference we use for a lot of the hardware build. So if anyone's interested in attempting this project, we've linked his article in the bibliography, and also Mikhail Klassen for his help and software. So this is the end of our presentation. Thank you guys for listening. I expect there will be a lot of questions because there's a lot of things a lot of like technicalities and details we didn't really have time to cover yet. So at this point, if anyone has questions. Yeah.
That was wonderful. Thank you, guys. So yes, we are getting some questions on the chat channel. I'm going to start with one of my questions. So, well, I had two questions, but you answered one of them, which was, how did you get the idea of doing this particular project? Since you answered that, my other question is, you guys are all in high school and doing this school project for your school. Do you guys, like all three of you, do you see yourself pursuing a career in astronomy?
I'd say for me personally, like definitely, because I say like I was the one who like kind of proposed this radio telescope idea at first to our club, and I say like I'm really interested in astrophysics and also radio astronomy as well, and I feel like this project has really given all of us, but like especially for me personally, I feel it really feels like doing real science. You know, like a lot of the stuff we learn in class is really interesting and all, but it's sometimes just fun to get out there, just kind of get really hands-on, be able to like build something, be able to observe with it. And I feel like this project's a really great way to kind of dive into astronomy and learn tons of new concepts, tons of new ideas, and kind of practice really being an astronomer. Anna and Connor, you guys want to add on?
I mean, personally, I'm likely going for the relatively, basic for us field of computer science. However, I'd definitely be interested in exploring other similar projects in astronomy. Artificial intelligence has already played a big role in finding exoplanets and other similar sort of uses in astronomy. So I'd definitely be interested in the future actively pursuing projects like those if they, arise.
Yeah, so I plan to study engineering next year at college, but I definitely plan to try to keep interest in astronomy and try to do it where I can, but maybe not as a career.
That's pretty cool. So I'll come to the chat channel questions now. Marianne has a question. She's asking, what was your budget? What did you spend? And how were you funded? Excellent presentation.
Thank you, Marianne. Well, our overall budget, I kept the cost sheet, came out to about, I think, $210. I'd say like the vast bulk of the cost came especially from the electronics, like the low noise amplifier. What bandpass combo was $40, the SJAA dongle was $30, and the rest kind of the hardware materials and stuff kind of just added up to the cost. I think that was about how much we were willing to spend because we, as high schoolers, we don't have that much, that large of a budget as like maybe professional astronomers do. And then how we funded? Well, we weren't really funded, I'd say. We did do some advertising at school last year by selling Chick-fil-A, which raised up some of our costs. But the rest of it, we kind of just tried to divide among the project numbers.
Cool. Hitesh is asking, did you observe any other regions than Cygnus A?
I think our observation period kind of started like January, February-ish of this year. So since it's since our school in our area kind of shut down in early March for shelter in place because we're in California, right? And then we didn't really get much of a chance after that. So I think primarily we were focused on like Cygnus A region. We did do some like kind of random observations at first, like in the Orion region, we did some. And the nice thing about like the hydrogen line is it's not like you're looking at an optical source or anything where you have to be at that target. Since the hydrogen line is kind of so common, you'll basically get a signal at a lot of the area of the sky, but it will just be varying in terms of like intensity.
Stephen has a question. Does your school have a wood shop, like with the table saw, drill press, etc.? And did you have any teacher or parent sponsor you and help you out?
So our school does have a wood shop, and we did build it inside the wood shop, but ironically, due to red tape, we could not actually use the tools because we're like a club and it's like separate. But we did we just brought like hand drills from home, and that was enough, and like like hand drills and like a saw from home to use in the wood shop, which has much nicer tools.
Okay.
But yeah.
Okay.
But yeah, we did. Yeah, we had a parent to supervise the stuff.
Okay, that's cool. Laura is asking, are there any places where you can vet and share your data with the scientific community as an amateur?
So while we personally didn't really look into publishing or sort of share our personal work as much, the forum that we mentioned, well, not the forum, but the group that happens to have a forum that we mentioned earlier, the Society of Amateur Radio Astronomers, was a huge help in attempting to plan out this project. So the actual forum is all archived on Google Groups. So there were a lot of resources there in terms of trying to find solutions to the problems that we were running into. So I'd imagine that groups like Sarah would have a pretty great impact on the ability to share our work with others if it came to it.
Hitesh has another question for you. Did you present your projects at science fair competitions like Synopsis Science Fair?
Well, I personally, using the Club Radio Telescope, I did a project kind of on my own, not with Anna and Connor, but and I did submit it to the Synopsis Science Fair this past March. I did end up winning 2 awards, I think, for it. It was like an IBM award and an award from SETI. And so I basically, what I did was not quite included in this presentation, but essentially like I observed kind of a region, the Cygnus A region of the sky, but the Cygnus A doesn't actually emit the hydrogen line that we detect. It's actually quite a confusing concept because hydrogen line emissions are basically from like gas clouds, and Cygnus A doesn't radiate that gas. And so my research project was basically trying to find kind of the real source of the hydrogen line emission. And I basically used like astronomical databases and kind of a lot of the similar process that we described above.
Cool. I don't see any other questions in the chat channel right now, but you are getting a lot of compliments. Everyone loved your presentation. It was really nice of you to put that together and present this project to us. And hope you keep at it. I'm gonna stay on the channel for a little bit more if anybody has any other questions. Let me just ask that one more time. Oh, and also somebody recommended an app called Distant Suns if you want to check that out. I do not know right now what was the context there, but definitely passing on a message for you guys there.
While we're waiting for more questions to filter in, I'll just share our bibliography real quick. So I'm not sure if the Astronomy Association will share a presentation, but these are like the links that were really important in our project. So the first one's, as I described before, the John Wallace's article, which is really instrumental in helping our process and planning. And then here's a link to Mikhail's website with the software. And then here's a link to the Society of Amateur Radio Astronomers.
That's great. This is part of the presentation you sent me earlier, right?
Yes.
Okay, cool. So I do have a copy, and if anybody asks for it, I would be happy to pass it on. So let me probably just mention that here. And there was also a suggestion about using Jupyter notebooks to plot and publish your data. I don't know if you're familiar with that software.
Yeah, I think we've definitely heard of Jupyter Notebooks, but haven't quite had the time to take a look at it yet. But we will check it out.
Okay, that's cool. Well, there are more compliments rolling in, but I don't see any more questions coming in. So thank you for being with us today, and it was great to hear about your project. And we'll keep in touch. And whenever the club can reopen in person for in-person activities, we would love to have you come in and have a follow-on discussion if possible. So good luck with everything you have planned ahead for your future.
Thank you so much for hosting us.
No worries.
Thank you.
Thank you.
I think that's all for today. Good night, everyone, and hope you join us for the next talk. Bye-bye.
Bye.
Bye.
Yeah, we're off.